Hello everyone, welcome back to PC 301 workshop. And I suppose this is the 7th day of the workshop. We start with our first session, and we have with us Professor Neeldhara Misra from Indian Institute of Technology, Gandhinagar, and she'll be talking on computational social choice. This is the first talk, and she'll be giving another talk on the topic tomorrow. And yeah, as you can see, we have an interactive chat feed displaying on the screen itself. So I suppose Neil is fine if you will ask questions, or if they wish, they can type in the chat. But yeah, just to let the audience know that the message feed is there on the screen, public to everyone. And that's it. So let's get you started. Thank you for joining us, Neil. Over to you now.
Yeah, thank you. Thanks, Pratibha, and thanks to everyone who has joined. So I'm just going to make sure that the video is spotlighted just because I think that way it gets picked up in the recording. Okay, so great. This is going to be mostly a survey talk. I think a fair amount of story and some toy examples in today's talk. And in tomorrow's talk, hopefully a little more in terms of there'll be a greater focus on techniques with a slightly different context. And we'll kind of explore a couple of hammers that have been useful for knocking out a lot of problems in sort of the broad field of computational social choice. I'll just quickly show you this couple of paragraphs that are stolen from the ComSoc website. By the way, if you're interested in computational social choice, and you're not already working in it, then the ComSoc website is a great place to start. So I'll also share a link of these notes from where, I mean, essentially you can click through and find the website. So essentially, the idea is, so we will be exploring the first aspect that is spoken about here, which is the application of techniques in computer science, like algorithm design or complexity analysis, to the study of problems that are motivated by social choice questions. So at a very, very high level, I think social choice research is three broad verticals. I wouldn't say this is written in stone, but a lot of it gets classified usually under one of these themes. So we have voting, or things motivated by elections, where you have two groups of agents and you're trying to, and this one group is the group of alternatives that you're trying to choose from, and the other is the group of agents that actually express their preferences over these alternatives. And we will be talking about voting quite a bit today, so I'll not say very much more about it right now. The other two verticals include resource allocation or fair division, and matching problems. So we will be talking about fair division a little more tomorrow, and there essentially you have a common resource that you want to divide fairly among multiple agents. And the key thing there is that different agents may have different perspectives, or they may have different valuations for the same common resource. And you want to ensure that you divide the resource in such a way that everyone is somehow happy. And of course, what does happiness mean? I mean, it's both a philosophical and a practical question, and we will see multiple formulations, and we'll try to tackle them from mostly an algorithmic perspective. In the matching problem, you are talking about two sets of agents that you're trying to match to each other. Typically, this comes up in the context of job allocation markets, or hospitals and residents classically, or even if you think about students trying to get into colleges of their choice or universities of their choice, all of those kind of fall under the broad umbrella of matching related problems. And again, there you want to make sure that there is some sort of concept of getting to a matching that is a happy matching for everyone. So both sides are kind of happy with what they got. And usually a key notion of capturing happiness is the so-called stability criteria, but there are also many other things that we may want to be looking at. So I don't expect to be talking about matchings very much in this sort of two overview talks, but I will say that there are a lot of problems in matchings that have only recently, started been explored under the sort of parameterized through the parameterized lens. And I think the overall the overarching point of these talks, or the overarching takeaway already, is that I think there's a rich set of problems that arise from these various ComSoc domains just waiting to be explored through this lens. And of course there is quite a bit of work along those lines already. But I expect that, there's also plenty to be done, and I hope that you get inspired to, work on some problems that you might discover from here. So I want to talk about like the broad voting setup. So let me just show you this sort of kind of the way I think about the whole field of voting. I think there's a lot going on here, so it's not going to really be possible to really capture all the different aspects in a talk like this. I think you could, and there are indeed entire courses and books on the topic. So I will just attempt to give you the highlights that sort of keep coming up frequently. And so with that disclaimer, let me just say that on the right, you will see the kind of problems that people like to worry about in the context of voting. So, so just to remind you, the setup is that there are typically a set of alternatives from which you are trying to choose some sort of a winning alternative. We'll come to, in fact, even the notion of a winner can have...
I don't know, somehow we can't read your slides. Like, it is very blurred.
Oh, really? It says I got a message from Zoom saying that my internet is unstable. So maybe that's why, because I'm able to see them.
Maybe that's
Okay.
Yeah, I think it's not very clear.
Like I just, like for example, left hand, all the blue thing, I can't read a single thing.
Oh, okay. All right. So I am not sure, but is it better now?
It has improved, but I think it could still be slightly more clearer for readability.
Okay. So just give me a second. I've tried to zoom in.
Yeah.
I'm a bit surprised because even with the previous thing, it was okay on my end. So I'm assuming that it's a network thing.
Could be a network issue, most likely. Yeah.
Yeah. Let me know if it's better now, and I'll proceed once it's a bit clearer.
Like I can see winner determination, control, bribery, manipulation, and lobbying. For the right ones.
Yeah, that's okay. So the ones on the left, I've kind of hidden them now because I've kind of zoomed in. But is it okay? Is it?
Yeah, but the ones on extreme right, like computational, axiomatic, and type of outcome, it takes like a bit of guessing and a bit of...
Okay, all right. Yeah, that is a bit strange because just give me a minute. I mean, it shouldn't be like that, so that's why I'm just pausing here.
Maybe, I mean, stop and restart the screen share or something like that. Or you're actually on videos.
Yeah, I'm on video, so I'm stopping and restarting the video.
No, it's still the same actually.
Okay. All right. So it's a little bit unfortunate, but maybe I will. Yeah, I'm just trying to see how you guys are seeing it. So I don't know from where I can do that.
I can
check the YouTube live stream.
I can send you a screenshot.
Oh, I see. No, I saw it on the, I'm seeing it on the live stream right now.
Okay.
It does look a bit,
yeah.
This. Okay, all right. So I think, as I said, I just hope that it will fix itself because this is, because the way I'm seeing it on my Zoom, it's kind of fine. So, but okay, this is sort of the story part, so it doesn't really require you to be able to see. Let me just.
Yeah, maybe you can continue for a minute or two, and maybe the network will stabilize, and else we can take a call on what to do.
Yeah, can you just to be sure though, can you tell me if like if you're able to see this clearly, or is this also blurred?
No, this is quite blurred. Okay, It improved slightly. Yeah, it's improved slightly now. Yeah, it's readable now. Did you do something?
No, I didn't. I think it's just network
Maybe it's
fluctuation.
just a network, and now it's all readable. Like there's a very slight blur, but it's completely readable.
Okay, good. Is it the same for the
Yeah,
mind?
yeah, yeah, it's readable. Perfectly fine now.
Oh, thank goodness. Okay, hopefully that was a temporary thing.
Yeah.
Okay, all right. Thanks. Great. All right. So,
Okay, just a small minor suggestion. Sorry to interrupt. Yeah, maybe since this is video, hence it might be getting more affected by the bandwidth. So maybe not move the content too much because it happens in a video feed
sure. Yeah, that's a good point.
if it's avoidable. Yeah. All
Yeah,
right. Sure.
I will try and do that. Let's see. I mean, part of the point was I think the reason I switched out to this was because I get to play around a bit, but yeah, I'll try to
Yeah,
control.
it's readable now. For now, it's yeah, perfectly fine.
Okay, yeah, just definitely let me know in the chat.
Sure, sure. Yeah.
Changes. Um, Okay, so as I said, this is like a broad, like lay of the land sort of thing. I think one of the most fundamental problems in voting is the issue of winner determination, and we will talk a little bit about specific voting rules in a bit. But even within the context of winner determination, there are sort of multiple issues that you might want to think about. So for a proposed so I think what I was saying before we had these technical glitches was that I just wanted to recall that the setup was that you have two groups of agents, alternatives and voters, and voters express their preferences over the alternatives, via let's just call them ballots for now. And you could have different kinds of ballots. So for instance, ranging from least expressive to most expressive, bottom to top. So for every alternative, a voter could simply say yay or nay, like him or not like him. So these are approval, typically called approval ballots. You could say I'm neutral, I like or I dislike. Those are ternary ballots. You could list your top K preferences, or you could give an entire ranking over the set of alternatives. Depending on the application scenario, you might be interested in different models of expressing preferences. In fact, sometimes when the number of alternatives is large, you might even be interested in questions of elicitation, because it's rather expensive for a voter to even give his entire preference, because it's like this big ranking. So the question then becomes, can you ask the voters easier questions about, say, outcomes of pairwise preferences to figure out what their overall opinion is. But by and large, just coming back to the winner determination problem, the idea is that voters express their preferences over alternatives using one of these methods. And you're typically interested in either design issues, how do I come up with a mechanism for determining the winner, which satisfies some nice properties, which may be given by axioms that you might be interested in. So here are some popular axioms that people consider. I don't want to go into this because this is not really the focus of this discussion. But given a particular mechanism, you may be interested also in how expensive is it to compute the winner using this mechanism. So that is the de facto search question in the context of winner determination. But in some situations, you may also be interested in the verification question. So given a particular outcome, is this an optimal outcome? And also while at it, I think I should also mention that you may be interested in multiple kinds of outcomes. You may be interested in a societal ranking that reflects a ranking over all candidates. You may be interested in a committee of size K, or you may be interested in just finding a single winner. So this is essentially, so depending on the type of outcome, depending on the type of preferences, and depending on the problem that you're interested in, you have a sort of a specific winner determination problem. The other four problems here are more, in some sense, more negative questions, where from a computational perspective, I think one is really interested in hardness results. I think it's a good thing if it's hard to figure out a manipulation strategy or a bribery strategy and things like that. Again, in the interest of time, I'll not get into the definitions of all of these different problems, but this is just to say that there are all of these different questions which kind of address strategic issues, the issue of whether people can either misreport their preference or preferences, or persuade other people to change their preferences, and essentially influence the outcome of the election. And again, here there are both computational and axiomatic issues, but from a computational perspective, this is one place where showing hardness results would actually be a good thing. Again, coming back here, we did talk about ballots in terms of the kind of settings that people like to explore. We sometimes worry about whether we actually have all the information that we need at hand or not. And sometimes we have to work with partial preferences. And when you're working with partial preferences, you end up worrying about problems like necessary and possible winners. This is usually, again, the broad setting is understanding the problems with when there is uncertainty. So the possible winner questions typically ask if it's possible to complete the information in such a way that it's consistent with the given information, and then a certain outcome happens, versus the necessary winner questions usually are phrased as follows. Is it the case that under every possible completion of your partial information, a particular outcome manifests? So you might be interested in knowing if your favorite candidate can win or will definitely win given some partial information. So we've already talked about the kind of ballots that people can give. In terms of these four problems here: control, bribery, manipulation, and lobbying. Your desired outcomes may be constructive or destructive. Sometimes you're interested in making something happen, and sometimes you're interested in ensuring that a particular outcome does not manifest. So you may be interested in making your favorite guy win, or you may be interested in ensuring that a least favorite person does not make it, and it's okay if anybody else does. So those are the two sort of broad flavors in this context. And I think I've already mentioned that we look at both design and algorithmic issues. All right, Tom and Jerry for all of you. I don't know why my phone wasn't on silent, but okay. So coming back here, this is something that given time, I'd like to talk about a little bit at least. So just like with graph problems, we are interested often in looking at special classes of graphs in the context of elections. Also, we have some interesting structures that are motivated by often actual political theory, and sometimes sometimes by real world data, and so on. And again, I have separate slides for the definitions, so I won't belabor them here. But again, this is just to say that a lot of these problems that turn out to be computationally difficult turn out to be tractable when you make certain additional assumptions about the input. In the context of parameterized explorations, here are some common parameters that are considered. Usually the natural ones are the number of voters or candidates, but sometimes you're also interested in the different types of voters or candidates.
Neil, your voice suddenly went down.
Okay, again, it shouldn't have. It's
We could hardly hear.
Oh, since when?
Right.
Just a few, I think, few seconds after your phone ring, after that.
Oh, okay. Are you able to hear me now?
It's still kind of low. Like, are you using the earphone, or maybe you could come closer to the microphone?
I'm just using a regular microphone, an external microphone. Again, let me just mute and unmute myself.
We can just barely hear.
Okay. Is it any better now?
Yeah, yeah.
Let me just check.
Yeah, it is. It's a bit. If the audience can mention, is the voice okay for that? Can you try saying something, Neil? Hello?
Okay, I'm continuously talking.
Yeah.
Are you able to hear me
Yeah.
now?
Now you're back. Yes, and your voice is clear, loud and clear.
Sorry, yeah, I have no idea what happens. Sorry. Sakit, unfortunately, okay, I mean, hopefully we won't have too many more technical glitches. Really sorry about that. But okay, so assuming, so can somebody confirm in the chat if the audio is okay? All right. Thank goodness. Okay. All right. So as I said, some of the common parameters that we're interested in are so apart from voters and candidates, which are the natural ones, sometimes this natural notion of solution size, or given that we talked about restricted domains just a minute ago, you might be interested in distance to triviality parameters. So for instance, what if your solution is close to being single peaked or close to being single crossing? That's something that people do look at, and it's quite interesting. And we are also often interested in what happens. So these are called high multiplicity problems, where you only have while the number of voters can be large, the number of distinct votes is small. So essentially, these are like weighted problems. So you have a small number of voter types, and each one of them could be, each one of those types could be pretty large or unbounded in number. Sometimes, so I'll come back to parameters inspired by structure and in the context where it comes up. But I'll also say that graph parameters often come into play because although I didn't mention it explicitly, there are quite a few problems where we also have a graph associated with either the alternatives or the voters. And in that context, one is often interested in what happens when the graph in question one is interested in parameters related to the graph in question. I'll just say one sort of popular example of this sort of thing is the gerrymandering problem, where you are trying to do some sort of redistricting for political gain, and usually there is an underlying graph that describes a network on the districts that can be merged or split. And often it makes sense to think about graphs that are planar in this setting, for instance. So that's one example of when graphs come into play, and usually graph parameters make sense in that context. So, all right. So I was going to talk about some specific examples of voting rules and so on, because we lost some time in the tech issues. Let me just go on to the first concrete example that I want to talk about, which is a lobbying sort of problem. This is just, as I said, a sample problem, just to get a feel for the sort of things that one might be interested in. And because the results here are, I think, cute and simple enough to work out, this is one thing that I would like to do, hopefully interactively. So let me just see if I can go back here. So all right, so here we are looking at a setting of essentially approval ballots, and so typically one has an electorate that's voting over multiple alternatives, and their votes can be thought of as yes or no votes. And the lobbying problem is the question of whether we can change a few votes to get all issues accepted. This is sort of a special case. You might say that you're interested in a fixed subset of issues or a fixed subset of alternatives, and you want to get those accepted. And for simplicity, I'm going to say that an issue is accepted if let's say more than half of the voters vote for that issue. Okay, and for now, let me just assume that the number of voters is odd, although it's not it's not a crazy assumption. We can work around it. Okay, so is the problem statement clear? So the input is this n by m binary matrix where n denotes the voters and m denotes the issues. And what we want is we want to know if we can influence at most k rows or change at most k rows so that in every column we have a majority of ones. So is the, please give me an indication in the chat if the problem statement is clear, because we will be discussing this for the next few minutes. Okay, great. Cool. So, let's first talk about parameterizing by the number of voters. When you parameterize by the number of voters, it's straightforward that you can sort of brute force and guess the rows that you want to change. But you might ask if you can do better, and it turns out that you can do significantly better under ETH, and this is something that we get by a reduction from vertex cover. So let's think about how this reduction might work. So again, let's just keep the problem in mind. We want to change at most k rows to make every column. So as I said, let's just assume that we want all issues to be accepted. That's the goal of the lobby, and we want a reduction from vertex cover. So let's just think about this for a minute. Okay, so here's the overall approach to this reduction. What I want to do is I want to use the incidence matrix of G. So the incidence matrix of G is going to have m columns and n rows. So column for every edge, and we're going to have some dummy rows at the bottom and some dummy columns at the end. So the reason for having dummy rows is to basically say that we want to force some rows to be changed. And in fact, let me even say up front that the number of rows that we want changed from the incidence matrix is n minus k. And these n minus k rows, actually, it may be also convenient to think of this in terms of independent set. So I want those n minus k rows to correspond to an independent set. In particular, I don't want to knock out 2 ones from any of the columns in the gray area. Okay, so I want every column in the gray region to have a majority number of ones, and I want the chosen rows in some sense to correspond to an independent set of size at least k. Can we think of, so in particular, okay, let me also mention what the dummy columns ensure. The dummy columns ensure that the changed rows only come from the gray region, that we never that we never change something, we never have to change a dummy row. How do we do that? Well, one way of doing that is to say that the dummy columns have a single one, so they're very sparse here. Okay, so every dummy column and every dummy row has exactly 1 1. What does that force? That forces that if you changed, I mean, you would, okay, so you would be forced to change things from the gray area to achieve a majority across all the columns. So let me just make this. So this was the point where I wanted to pause and ask for suggestions for, how would you, so this is like a bit of a puzzle, and I think it's wholly possible to puzzle this out. So can we just maybe pause for a couple of minutes here before I show you exactly what the dummy rows and columns are doing via both a worked out example as well as a more detailed schematic. But right now, this is like a bit of a, I mean, I haven't told you exactly how many rows to throw in and exactly what to do in terms of the zeros and the ones. So any thoughts so in some sense, what we want is we want to force a majority. So the question is, how do we set this up? How many additional rows would be useful, do you think? Any thoughts about that in the chat? So just to recall, actually, I don't think the example is a complete giveaway. By the incidence matrix, I should say that the incidence matrix essentially gives you, for every edge, it gives you 2 1s at the endpoints of the vertex. Okay, so I think this example here should tell you the structure of the incidence matrix. It has, for every edge of the graph, we have 2 1s. Corresponding to the endpoints of the edge. The rows, of course, are indexed by the vertices, right? So yeah, I think the way this example is, I haven't told you exactly how many dummy rows and columns to add. So what do you think should be the right number of rows and columns to add to force a change uh, within the incidence matrix in such a way that the changed rows correspond to an independent set, so that the unchanged rows correspond to a vertex cover? So notice that if I can get, if I'm allowed to change n minus k, so that's going to be my budget, by the way. So if I can change n minus k, if I can change n minus k rows, I'm actually going to, in all the columns corresponding, to the voters, in all the columns corresponding to the edges, I'm going to actually get n minus k extra ones. And the question is, when does that become a majority? How many rows would it be safe to add, so that when I add n minus k ones, which in the columns, I sort of get a majority. So what I'm looking for, so just to make the question explicit, my question is, how many rows do you think I should add here? Let's forget about the columns for now, because the columns just are useful for enforcing that all the action happens in the right place. Okay, so maybe let me just go back to the description here, and maybe this will be a bit clearer. So what we are going to do is we are going to add n minus 2h dummy rows, so that the total number of rows is 2 times n minus h, okay, where h is the size of the vertex cover that you're looking for. Okay, and as I said, the ones that you add among the dummy rows and columns, they are just essentially, that's a bit of a gadget to force the action to happen in the gray area, which is the part of the construction that comes from the vertex cover instance. So that helps us in the reverse direction. So let's not worry too much about the structure of the zeros and ones in the dummy area. That's in the dummy region, because as I said, that's more of an enforcer than anything else. But the idea is that, let me just go back here. So if you look at what's going on in any column that corresponds that corresponds to an edge, there are exactly 2 1s. And notice that you have n minus h, you have a budget of changing n minus h rows. So assuming that you only change the rows from the gray area, if you end up if you end up picking up both of these rows that correspond to the endpoints of an edge, then essentially the total number of ones that you can get here after all your changes are done is still only n minus h. But remember that you want a strict majority in every column, right? Because you want a strict majority in every column, you cannot afford to pick both the endpoints of an edge in your set of changed rows, right? So therefore, the n minus h things that you pick must correspond to an independent set. They cannot contain an edge entirely, right? So that's essentially the idea of the reduction. You are, again, just to recap, you have the incidence matrix of the graph. You add essentially n minus 2h dummy rows to ensure that the total number of rows is 2 times n minus h, and you give yourself a budget of n minus h. And now if you just had the rows, this may or may not work because you may not be changing interesting rows. You may be changing the dummy rows in your lobbying, which don't tell you very much about the graph. So essentially you add some dummy columns and you add ones in this sort of a diagonal fashion here. What this does is that it essentially enforces that all the changes happen in the upper part of the matrix. In particular, they all happen. So by the way, once you pick a row, you simply end up changing all of them to ones. You can do that greedily. It doesn't hurt, right? And okay, so I'm sorry that despite having tried to set this up, I think I just missed Akanksha's message earlier. So thanks for that. I think n minus 2k plus 1, this just exactly makes sense. I think, yeah, it's just off by 1, but yeah, sorry for acknowledging that late. Anyway, so I think hopefully the main idea of the reduction makes sense. So just to recap, recall that every column in the interesting part of the reduced matrix has 2 ones corresponding to the endpoints of the edges and zeros everywhere else. And what you need is strictly more than n minus h ones per column. And because you need strictly more than n minus h ones per column, and your budget is n minus h, it would be wasteful, or it would be dangerous for you to pick 2 rows that correspond to the 2 ones. So if you pick n minus h rows, they should not touch both of these ones. That's kind of the main idea of the argument. Of course, in the forward direction, after you set this up, you just pick the vertices corresponding to an independent set, leaving the rows corresponding to a vertex cover completely untouched. This has the effect of essentially guaranteeing that you get a majority everywhere, right? Because you have flipped n minus h, at least n minus h minus 1 zeros to 1. So for a given column, you at least one of the original ones is untouched because you flipped an independent set. So one of those ones is definitely there. And on top of that, one of those ones was from an unaffected row, so it remains there. And other than that, there were n minus h affected rows, which were either flips from 0 to 1, or they were like one of the original ones that remained a 1. So you get strictly more than n minus h ones in each of these columns. And of course, in the dummy columns, you have 1, 1 from below, the way this is set up, and you get n minus h ones on the top. So n minus h plus 1 is the total number of ones per column in the dummy columns as well. As I said, in the reverse direction, the one part that I'm not making very explicit is the fact that the red gadget forces the action to go on the top. Once you ensure that, you essentially, the argument that we just made a minute ago ensures that the changed rows correspond to an independent set. So hopefully that made sense. So we have here, again, a situation where the trivial algorithm is the best that you can hope for. Now, there is, you could also think about the solution size as the parameter. And again, there is an easy brute force solution because you could just guess the rows that you want to pick. But you also have a W2 hardness reduction from dominating set, which is in a very similar spirit. And Again, in the interest of time, I want to move on to parameterizing by the number of candidates. So let me do that. We could come back to this, or if anyone's interested in taking a look, we could come back to this. But again, it's an interesting puzzle. Just to it's in a similar spirit. You want to set. I mean, you borrow the in this case, not exactly the incidence matrix, but you set up a portion of the matrix that exactly reflects the adjacencies from the graph. And then you set up extra dummy rows and columns to force a certain amount of change in the serious part of the in the serious part of the matrix. So so I think this is a good problem to think about offline, or maybe we could come back to it if we have time. Okay, so let's look at parameterizing by the number of candidates. So here, again, I don't know if there is, so let me just recall the problem statement. So we're trying to change at most k rows, and it's not clear if, it's not clear that you can, for instance, do some reductions. The columns are really quite independent from each other. So it's not clear if you can do some reductions so that the number of columns is bounded by a function of the number of voters, and then maybe you can apply the FPT result on the number of voters. It's not clear to me if we can do it that way. And also it turns out that there is no polynomial kernel with respect to M and K as well. So that's another hardness result in this context. But I think it's interesting to think about if there's a natural FPT algorithm. What I'm going to show you now is an ILP based algorithm. And it turns out that this is actually something that's true of many problems in social choice, that you get FPT algorithms by formulating an appropriate ILP. Okay, so I'm going to hopefully just illustrate this method, and this is something that we will pick up on and dig a little bit deeper into tomorrow. We'll be looking at somewhat ILP on steroids kind of methods. So, so this is sort of a prelude to that. But it's an interesting question to think about if there's a natural algorithm parameterized by the number of candidates. I was at least nothing obvious that that seems to strike upfront. But again, do let me know if you can think of something that occurs to you now or later. Let's think about how we will come up with an ILP-based solution. So recall that for the ILP-based solution to work, you need the number of variables to be constrained as a function of the number of as a function of your parameter, which in this case is the number of candidates. So again, any suggestions for what the variables should be? Is there some? So we are interested in, again, the solution is the number of rows that are affected, right? So what can we do in terms of capturing that in an ILP with a bounded number of variables, where the bound is in terms of the number of candidates? What is a natural way of relating the number of voters to the number of candidates?
A subset of voters that are approved by the same, subset of candidates that are approved by the same voter.
Subset of candidates. So every voter can be thought of as a subset of candidates. Is that what you meant?
Yeah.
Sorry, feel free. I didn't mean to cut you off if you wanted to elaborate.
No, that's all.
Yeah, okay, cool. So yeah, so I think so every voter can be thought of as a subset of candidates. And I'll just say that this is what I meant earlier when I said that you might be interested in the number of voter types in certain problems. So here also we will try to rely on voter types. So what we would be interested in is understanding how many voters of each type were hit by the solution. The solution picked up how many voters of each type, and that can be expressed naturally as in terms of ILP variables. So let me just throw in some notation here. So let xi be the number of rows of type I that are affected by the solution, and let ri be the number of rows that are of type I in the given instance. Okay. Also let Gj be the target number of ones that are still needed in column J. So in every column, you have already a certain number of ones and you are a certain distance away from majority. So in column J, let's say Gj is the number of ones that you need to convert it into a majority column. So what should the objective function be? So let's just say that K is, it's probably not visible now, but K is the solution size. So when I say affected, I mean affected by the solution. So our budget is K and Xi is the number of rows of type I that are affected. So there's sort of a natural, okay, you could either think of it as an objective function where you want to minimize something, if you want to minimize the number of affected rows, or if you want to think of it as a decision problem, you could just think of it as a feasibility constraint. So although I've written objective function, you could think of it either way, yeah. So what expression in terms of Xi captures the cost of the solution? Yeah, the sum of all Xi's, thanks. The sum of all Xi's captures the cost of the solution because each Xi for each type denotes the number of affected rows. So this is your objective function. And as I said, you could think of it, you could either think of it as minimizing the sum, or you could think of it as a feasibility constraint where you're saying that the sum of the Xi should be at most K. Okay, this is subject to what? What do we need? What are the constraints on the rows? And by the way, I didn't talk about a bar ij because we don't need it for a bit. So, but what should the constraints be in terms of? So we have these xi's, but so what? So every xi tells us that from type I we need so many voters to be affected. We need so many voters to be picked by the solution. So what is a natural relationship between xi and ri?
Xi is less than equals Ri.
Xi is less than or equal to Ri because you cannot pick more than the number of available rows. So the number of things that you pick of type I have to be at most Ri. And of course, there's a non-negativity constraint. Yeah. Okay. Now, for this to be a solution that actually works, right? So for now, we have something that is feasible. It's within our budget, and these many rows are in fact available to us, so we can pick them. But this could be any combination of rows, really. So how do we say that using a linear constraint? How do we say that the chosen rows, like if we pick so many of this type and so many of that type and so on and so forth, if we put all of that together, we actually trigger a solution. We get a majority in every column. So these will be captured by column constraints. So we want, for every column, we want to say something. So what do we want to say? For every column, so here this notation may be useful. So a bar ij denotes, a bar ij is 1 if I has a 0 in column j. So if I has a 0 in column j, that's a good thing for us. So notice here that I is a type. It's not a voter index, but it's a type. And this makes sense because all voters of the same type have the same, they have the same 0, 1 signature, right? So let's say a bar ij is 1 if and only if row I has a 0 in column j. That means that for column j, this is a good type for us. If we hit this type, then we gain 1 in column j. So what should the column constraints be? So for every j, we want to say something.
Sum over I aij multiplied by xi is greater than ci.
Okay, so right, aij times xi sum over I. So yeah, you're summing over all the types, and so you want to measure your gain from each type. So you do this for every column separately. So you're going to have a separate constraint per column, but let's fix our attention on column J, and then we want to say that let's count the gain that we get from all the types I. So we sum over all the types, and for each type we take xi because that's the number of rows we manage to hit of that type, and we multiply that by aij bar. So of course, if it's not a good type for us, then this xi does not add any value, so it gets knocked out. But if it's a good type for us, then this xi actually gets added to our solution. So this sum here counts the number of ones, the number of extra ones that we have created in column J, and we want this number of extra ones that we have created in column J to be at least Gj, where Gj is the target number of ones that were needed in column J to begin with. So that's excellent. So thanks for helping me out with setting up this ILP. So we have, as you can see, we have 2 to the m variables, and we have a certain number of, I think we have n plus m, m plus 2 to the m constraints. So n is actually depending on the situation, n is a better or a worse bound. So anyway, we have a constraint for every type. Some of these constraints may be moot if essentially ri's are zeros, then you don't have to add those constraints, but that's a minor point. So overall, this gives us a FPT algorithm, and the running time is not so nice because again, it's this big ILP hammer that we are using, and I think it's probably still open. And this is something that is true for all of these problems that are solved using ILP, and I think there are very many of them, especially in the literature of voting in COPSOC. And it's interesting to know if there are more natural or more combinatorial approaches that give us better running times. And I think in general, lower bounds are also fairly wide open for many of these problems. So I did have like a few more things that I wanted to get into. In particular, I wanted to tell you a little more about the very rich literature on restricted domains. And I thought I will switch out to the slides, but I'm just looking at the time, and I think I am nearly over time here. So maybe essentially what I was hoping to communicate with just this one sort of sample is that first of all, that there are a fair number of natural parameters to dig into for most problems in this area. And many of them are solved using like these big hammers. And in fact, I think it's been stated in multiple places as to whether there are more, natural sort of techniques that give us better algorithms. And can we also tighten up things on the lower bound side? So there aren't that many results about lower bounds, for instance. So hopefully I've sold this idea that, this is essentially a very rich collection of problems that is, I would say, somewhat underexplored from the parameterized lens. And hopefully this, sampling gives you a sense of the kind of games people play here. As I said, tomorrow we will look at a slightly different context, a different set of problems, and again, hammerish techniques for solving them, and we'll explore the issue of the sort of things. I think I'll have a more explicit list of open problems for tomorrow that hopefully will be a good place to stop with the survey. So all right, so once again, my apologies for the technical issues that we ran into, but in the couple of minutes that we have left, if there are questions, then I'm happy to look at those.
Thank you so much, Neil. It was a great talk. And yes, we do have time. If there are any questions, people can just unmute themselves and ask right away. Or if not, if you prefer chat, you can type in the chat.
Hi Neil, this is Sandeepta. I just wanted to ask a general question. So, are there problems in the, since you mentioned at the end, restricted domain, so are there problems in the restricted domain which are hard and can be addressed by using ILP, like the similar kind of method that you showed?
I think there are some. So usually, most results with regards to restricted domains, and especially single peaked and single crossing domains that I'm aware of, are positive results. Although for these so-called Euclidean domains, which are a bit more general, I think there are some hardness results. I think there are some exceptions, though. One notable one that I remember offhand is. I think the NP completeness of determining Monroe committees, even on I think even on single crossing profiles or something like this. So in this context, I think it makes sense to see if the machinery helps get better algorithms in the context of restricted domains. It's a good point that I don't know of ILP formulations that explicitly take advantage of restricted domains. I don't know if there are maybe others who are here who know more about this than I do, but I don't recall having seen an example of an ILP being used to. Okay, I think that, okay, so I should make a quick exception to that. I think there are some interesting polynomial time algorithms that come about by observing that the
Yeah, the
that certain,
intermodularity of the ILP.
sorry.
Yeah, no, no, continue.
Okay, so yeah, so I think when you look at some natural constraint matrices that arise when you write down like certain ILPs, assuming that you are coming from a restricted domain, then those constraint matrices turn out to be, I think, totally unimodular or something
Yeah,
like this.
yes.
And in that case, those can be solved much more easily, and I think in fact in polynomial time. So that is something that is kind of known. But for problems that are hard, like NP hard in the setting of restricted domains, the ILP having like more nuanced structure and helping out. I don't recall this off the top of my head. No, so that's a great question. I don't know off the top of my head. Yeah.
Mhm. Thank you.
Any more questions?
Okay, so I'll just point out like a quick problem in this context that I'm not sure has been looked at specifically. So these are approval ballots. So the restricted domains that I mentioned are usually defined in the context of rankings. But even for approval ballots, you can think about special kinds of matrices where the ones, for instance, form. So there are these. There's this notion of a COP, consecutive ones problem. So you assume that the matrix is such that or you can rearrange the columns in such a way that in every row the ones are all consecutive. So that's a nice sort of special case, and I'm not sure if for these problems if that's sort of an interesting. So there is another paper called Structure and Dichotomous Preferences that talks about this is an interesting special case, and there are many other special cases that they also point out. So that's essentially restricted domains in the context of approval ballots. And I don't think lobbying in particular has been looked at in the context of restricted domains. So that may be like an interesting direction to think about for a bit. And once that is sorted, then I think distance to triviality also makes sense. Like you want to know if your matrix has these special properties plus some noise, then parameterized by that noise, however you choose to define it, extra rows, extra columns, or edits, or whatever, then parameterized by that noise, is this problem easy or hard? So I think those are some fairly natural questions to think about already in the context of this problem. But if you go back to the bitmap, I'll not show it to you again because it seemed to trigger some issues last time. But essentially, the literature on these problems is very, very vast. And for most of them, I think the classical complexity has sort of been addressed in some form. And I think slowly the literature on parameterized and approximation approaches, of course, growing, but I think there's really a lot of potential to bring in some of the techniques that have been explored in the school to many of these problems. So yeah, I think I'll stop with that thought. And maybe we can, maybe it's a good time to break so that we can come back at 5. Yeah.
All right then. Thank you so much, Neil. Thanks for the talk.